This is section 13.3, the rate law, the effective concentration on reaction rate. So the rate of a reaction often depends on the concentration of one or more of the reactants, but not always. And so we can write a rate law, which is the relationship between the rate of the reaction and the concentration of the reactant. So we're going to start out by just looking at a very simple decomposition reaction where you have one species, one reactant, and it's decomposing into some products. So that just gives us one reactant that we have to deal with. So we can say that the rate is equal to some constant that we call the rate constant, very, very clever, catchy name there, times the concentration of that one reactant raised to a power n. And that's the general formula for a rate law. And so n, we could say, is the reaction order. One. No? You're not going to do it? Why? Why, computer? Why do you hate me? Oh, hey, look at that. That was...
Don't ask any questions.
Okay. So the way you get the taskbar to disappear is you touch the screen. Okay, we learned something. Okay, now on to reaction order. Again, here's the rate law. The reaction order depends. Good grief. I should probably start over. I'm not going to. The reaction order determines how the rate is affected by the concentration. And so we're going to talk about three different situations: zero order, first order, and second order. For a zero order reaction, n equals 0. And that means that the rate is independent of the concentration of A. Because if we have the concentration of A raised to 0, we're saying the rate equals a constant times A raised to the 0 power. What is anything raised to the 0 power? It's 1. And so that is equal to the rate constant. And so a zero order reaction, the rate of the reaction does not depend on the concentration of the reactants at all. In a first order reaction, n equals 1, and the rate will be directly proportional to the concentration of A. So that ends up being, I'm pretty sure this is all in the next slide, but oh well. So a constant K times the concentration. Second order is proportional to the concentration squared. So it is more dependent on the concentration. And there are other orders that are possible. You can have a 1/2 order or 1.5, but these are the most common ones. This slide shows two different graphs. One is showing the reactant concentration versus time for the three different types of reaction. So for a zero order reaction where that exponent is 0, we see that the concentration changes linearly with time. It makes a straight line here. For a first order reaction, it changes less and less as time goes on. And the second order is the even more so. That was just really lame. Sorry about that. This is rate versus reactant concentration. So here we have the rate in molarity per second. For a zero order reaction, the rate is going to be constant at any reactant concentration. There's no dependence on concentration. For a first order reaction, the rate is linearly dependent. So it's a straight line here. If you double the concentration, you double the rate. The second order is going to vary with A squared. Yeah, pictures, right? Should have just saved 1,000 words. A zero order reaction seems a little strange, doesn't it? That the rate of it doesn't depend on the concentration. Sublimation is an example of a zero order reaction. So here we have an illustration of It doesn't say what it is. Maybe that's carbon dioxide. And it's subliming. Remember, sublimation is going directly from the solid to the gas. The only particles that can sublime are the ones on the edges, right? And as one layer sublimes and goes off into the gas state, what's underneath? Another layer. Does the concentration really change? No, it's not really changing. And so a zero-order reaction is going to happen when the amount of reactant that's actually available for reaction is not affected by changes in the overall amount. The amount of the carbon dioxide in this block would be changing as it sublimes, but the amount that is actually able and available to sublime is not really changing, and so that's why the reaction rate doesn't change. Well, how do we determine what the reaction order is? Can we just look at the balanced chemical equation and say, oh, well, this is first order and that's second order? No, we can't. Reaction order is determined by experiment. And that's really important. I'm going to say it again later, but we can only find the reaction order by actually doing experiments. One method is called the method of initial rates. And what we do is we measure the initial rate of the reaction several times using different initial reactant concentrations. And we see how the rate changes when that initial concentration is different. So here's an example of some data for our hypothetical decomposition reaction. Here, starting with 0.1 molar A as our initial concentration, we measure it and we find that the rate is 0.015 molarity per second. If we double the concentration to 0.20 moles per liter, the initial rate changes to 0.03. So we doubled the concentration, and what happened to the rate? It also doubled. So when we went from this one to this one, that was times 2. And that's the same thing that happened. We did this over here. We're controlling the concentration and measuring the rate. And then here we doubled the concentration again, and what happened to the rate? It doubled. These numbers are relatively easy to look at and see that it's doubled, but you could just take 0.06 and divide by 0.03 and you'll get 2, right? So this is also doubling. So we double the concentration, we double the rate. That means the rate is directly proportional to the concentration. So the rate equals some constant times the concentration. What's the exponent up there? It's 1. Because we double one, we double the other. Okay? How could we determine what the rate constant is?
Do the initial rate divided by the concentration?
Yeah, we can use this equation, and we want to solve for K. So K is going to be that initial rate divided by the concentration. Does it matter which of these three we take? No. The reaction constant is constant, right? The rate changes all the time, but the reaction constant, rate constant is a constant. So let's just pick the first one. So the rate is 0.015 molarity per second, and that's divided by the concentration, 0.10 molar. The molars cancel out. Sounds like dealing with a dentist or something. I don't trust my brain to do math very much today.
Quick math? Or 3/20?
I don't like fractions. This is just 0.15. 0.15, and the units are per second, or second to the minus 1. Any questions? So sometimes we can just look at the initial rates and how they change with changes in concentration and see what's going on. So that was a first order reaction. Here, these are actually labeled for us, but let's look at what's happening here. What are we doing to the concentration of the reactant, going from 0.1 to 0.2? Doubling it. And then when we go to 0.4, we're doubling it again. And does that have any effect on the rate?
No.
No, doesn't change the rate at all. A zero-order reaction is not dependent on the concentration of the reactants. So that's how we can see that this is zero order. Changing the concentration does not change the rate. We've got this one over here. We double the concentration, and what happens to the rate? It quadruples. 0.015 times 4 gives us 0.016. Okay. So this is doing times 4 when this does times 2. And here we've doubled that again, and what happened to the rate over here?
Quadrupled again.
It quadrupled again. What if you look at the data and you can't figure out what the pattern is? Then what do? This method works pretty well for 0, first, and second order, but what if you end up with a half order? That's a little harder to find out. So this is our little trick here. If the order is not obvious, just looking at it, we can use this equation. What's going on here? We're taking rate 2. Actually, let me do this for a minute here. Just going to get rid of that. Ooh, isn't that fun? So, is it true that rate 2 is equal to a constant times the concentration of A at that point raised to a power n? That's the general form for the rate law, right?
Yeah.
So that's true. And that's also true, right? Rate 1 equals the constant times the first concentration raised to that power n.
Yeah.
So those two things are equal. So if we divide them, it's still equal. We took one equality and divided it by the other. Well, what happens then? Well, the k's cancel out, right? K over k goes away. That's 1. And now we can actually use this to solve for n. Because the one thing that's staying the same here is n. We're using 2 different concentrations. We're using 2 different rates. So let's do this on the second order reaction, plug some numbers in and see what happens. Which point do you want to use as number 2? We're going to use this table, and we're going to pick one line to be 1 and another one to be 2. Doesn't matter which one.
The first one first.
We could make the first line number 1 and the second line number 2. How's that? So rate 2 is 0.060, and rate 1 is 0.015. The concentration for point 2 is 0.20, and that's raised to the power of n. And I'm dividing that by the concentration of the first one. That's also raised to the power of n. Yeah, I don't know where I got that from. Thank you. I wrote the wrong number. 0.10. Yeah.
Okay.
Just seeing if you're paying attention. So now we need to simplify this. The exponents here are the same, and so this is equal to 0.20 over 0.10, that fraction raised to the n power. So now let's use our calculators. 0.06 divided by 0.015 equals 4. So we have 4 equal to 0.2 divided by 0.1, 2 to the n power. Now this turns out to be one we could do in our heads, right? You know, what power do we have to raise 2 2 to get 4? Well, it's going to be squared. What if we can't tell?
Do the other ones.
You do the other ones. Well, but what if n is not going to be a nice number? Natural. We're going to take the log of both sides. So we're going to take the log of 4, and that's going to equal the exponent times the log of 2. So if you have, it's math. I'm a chemistry teacher. I'm good at teaching chemistry. I'm not always that good at explaining math to you. But this is one of those math things that you can do. If you take the log of both sides, oh, I know how to write it. The log of x to the n is equal to n times the log of x. That's what I was trying to get at. So then n equals the log of 4 divided by the log of 2. Yes?
Do we put it in degrees?
Yeah, degrees.
Okay.
I don't think it's going to really matter, but we're not going to do radians or grads or anything like that. That's for crazy people. My apologies if you're one of those crazy people. We still like you, but I still think you're crazy. Okay, so the log of 4... Yeah, now the internet's giving me problems. The log of 4 divided by the log of 2. So you take 4 log divided by 2 log equals 2. Any questions? We're taking the rate law for one set of data, dividing it by the rate law for a different set of data. The constants are going to be the same, and the exponent is going to be the same. And the constants cancel out, and then we can solve for the exponent and find out what the order is that way. Let's talk for a minute about units for the rate constants. The rate constants are going to have different units depending on what order the reaction is. So let's figure these out. So for a zero order reaction, what are the units of a reaction rate? Molarity per second, right? And then we've got K in here, so I'm going to leave a blank for him. That's what we're trying to figure out. And what are the units of A to the 0? Well, this is equal to K, right? A to the 0 is 1.
Yeah.
So if this is equal to K, then the units on K must be molarity per second. You can write it that way, or you can write it this way. There's different ways to do it. So for a zero order reaction, the rate constant is going to have units of molarity per second. For the first order reaction, the rate is still molarity per second. And now we have what we're trying to figure out times molarity. So we need something in here that's going to give us the same units as over here. What's that going to be? One over a second, right? Second. Okay, so I don't think that was a very good explanation. Let's do it a different way. Let's solve for K. So K equals the rate divided by the concentration. Yes? Somebody say yes. Okay, thank you. The units of rate are molarity per second, and the units of the concentration are molarity. What happens when I simplify those units? I get 1 over second, or second to the minus 1. The m's cancel, but I'm left with 1 over s. Let's do the same thing for this second order. Here we're going to divide by a squared. So K equals the rate divided by the concentration squared. Well, the rate is molarity per second. Concentration squared is going to be molarity squared. So the molarity on top will cancel 1 from the bottom, but then there's still 1 on the bottom. So this equals 1 over molarity times second, or molarity to the minus 1, second to the minus 1. Units are your friends. The most important thing I learned in high school, well, maybe not the most important, the most useful thing I learned in high school was in physics as a junior in high school. My instructor taught us dimensional analysis and basically how to fake your way through physics using units. And it's just an awesome thing. So I'm just showing you this because the book does point out that the rate constant has different units for different orders. You can always figure it out if you need to. What if we have multiple reactants? Because not all reactions have just one reactant. So we're going to look again at this generic reaction. AA plus BB goes to CC plus DD. The rate is going to be proportional to the concentration of each reactant raised to a power. So the rate is the rate constant times A raised to some power m times B raised to some power n. M and n are not related to the coefficients in the balanced chemical equation. Remember, the rate law has to be determined by experiment. You can't just look at it and figure out what it's going to be. But however many reactants you have, it'll be the concentration of each of those, and they are each raised to a power. Those exponents could be the same, they could be different. When we talk about the overall order of the reaction, we're talking about the sum of these exponents, m plus n. So let's look at a couple examples. So for this reaction, hydrogen gas reacting with iodine to form hydrogen iodide. Here is the rate law. What is the overall order of this reaction? 2. We're going to take this exponent and add that exponent. 1 plus 1 is 2, right? What's the order with respect to hydrogen? What's the exponent on the hydrogen? 1. So it's first order with respect to hydrogen, and what order with respect to iodine? First order. Okay? I probably should have written that down, but the moment has passed. Here's another reaction. What are you doing, silly iPad? Hydrogen reacting with keep getting disconnected. Hydrogen reacting with NO to form nitrogen and water. What's the overall order? Overall, it's third order. 1 plus 2. What's the order with respect to hydrogen? 1. First order. And with respect to NO, second order. Okay? NO is one of my favorite compounds. For practice, determining the order and rate constant of a reaction. So here's our reaction. And it says the initial rate is measured at several different concentrations of the reactants with the following results. And from looking at this data, we have to figure out what the rate law is and what the rate constant is. Well, let's think about what's the generic rate law for this. Yeah, so the rate's going to be the rate constant times one of the reactants, that's what they're called, one of the reactants raised to some power, times the concentration of the other one raised to some power. So this is more complicated than that simple reaction we were looking at, but we can look at the data and find each of these orders separately. So let's first look at the CHCl3. When we change this concentration from 0.01 to 0.02, what are we doing to the concentration? We're doubling it. So that doubled. And this one stayed the same. We did that on purpose so that we could examine how it changes with the first one. And what happens to the rate when we do that? It's real close to doubling, right? Almost, yes. So let's see what exactly it is. 0.0069 divided by 0.0035, 1.97. Okay, so that is really close, and this is where knowing a little bit about significant figures is helpful. How many significant figures are in these rates? 2. And so if we were to round this to 2 significant figures, what would it be? It would be 2.0, right? So that is definitely close enough that we can say, yeah, that's 2. Because this is more real data. It doesn't always come out perfect, right? So we doubled the concentration and the rate doubled. That tells us the order for CHCl3 is what? It's 1. A first order reaction, the rate is directly proportional to the concentration. So that tells us that M equals 1. Now here, we need to figure out what's going on with Cl2. So we could compare the second line and the third line because here the first concentration is staying the same. We need that one to stay the same, so it's not going to mess with the effect of the other one. So from 0.01 to 0.02, we're doubling the concentration, right? And then we want to see what's happening with the rate there. Well, that's not exactly obvious. So 0.0098 divided by 0.0069, that gives us 1.42. Should we just round that to 1? No, we can't do that. That'd be nice, be simple, but yeah, not so much. Now what do we do? Do that rate over rate thing. So we're going to take rate 1. We're going to use this and this. And this is our concentration, and we'll call this one 1 and this one 2. And this is rate 1 and rate 2. I'll make it a different color. Maybe it'll be a little less confusing. So rate 2 is 0.0098 divided by rate 1, 0.0069. And that equals the rate constant times the concentration for that second line, which is 0.020, raised to some power n. Oops, n. So that's this n I'm trying to find over here, divided by the same rate constant, and now I'm taking this first concentration, 0.010, raised to the n power. You still with me? You see where I pulled all those things in from? So the k's cancel out. Those go away, and this is equal to 0.020 over 0.010 to the n power. So we actually already did this, looking to see what was going on, and it came out to be 1.42029. You don't have to write everything your calculator throws out at you, just write more than the number of sig figs. And 0.02 divided by 0.01 is what? 2. 2 to the n. So let's just double check that. Yeah, it's 2. So now we're going to take the log of both sides. But the log of 1.42029 is going to equal n times the log of 2. And of course, I ran out of space. 1.42029, taking the log of that, and then I'm going to divide by the log of 2, and that equals 0.50618, blah, blah, blah. Let's see if it comes out any better if I don't round that off. 98 divided by 0.0069 equals log divided by 2 log equals, and that comes out the same. That's really close to 1/2, isn't it? So that's really close to 1/2. So n equals 1/2. Yes?
So like right there, n equals 1/2. What if you were, do we have to do this again with like say another 2 numbers just to make sure it's still going to be that? Or once we find one number, we're just done. We assume they're all the same.
If you have good data, and in a problem like this, you can assume that the data is good, it's good enough to just use what we did here. You don't have to do it over and over again for everything. In more real data, it would probably be good to throw it in a spreadsheet and calculate the order with all the points. And then hopefully they'll come up and cluster around something nice. So the rate law then is, let's stick these numbers in here. It's the first one to the first power and the second one to the 1/2 power. That's the answer to what is the rate law. How do we figure out what the rate constant is? Well, here we've got 3 different sets of points. I'm sorry, 4 sets of points. Can't count. We could choose any one of those, plug in the rate and these concentrations, and solve for K. So I'm going to put that up here, just kind of because I can. Size will go up there. That's not what I wanted. Okay. So we're just going to make some space up here to do our calculation. So K is going to end up being the internet is just really not being kind tonight. K is going to equal the rate divided by the concentration of CHCl3 to the first power times the concentration of chlorine to the 1/2 power. Let's just use the first line. 0.0035. And let's put units in there because the rate constant is going to have units. So this is molarity per second and this is going to be, both of those concentrations are 0.1. So 0.010 molar to the first power, 0.010 molar to the 1/2 power. .0035 divided by 0.01 divided by 0.01 y to the x 0.5 equals, and this comes out to be the number 3.5. What are the units for that rate constant? We have to look at the units in this expression and simplify them. So this one up here in the numerator can cancel this one in the denominator, right?
Yeah.
Those will cancel out. And so then we've got molarity to the minus 1/2, seconds to the minus 1. Are those weird units? Yeah, they are. Sometimes we end up with weird units. But that's the rate constant. Now you could try this at home. If you use any of these other sets of data and plug them into this equation, you should come up with the same rate constant, right? So the rate constant is a constant. Any questions? Yes?
I'm sorry, this is something that's bothering me. You said that m equals 1, and I see that based off just the line 1 and line 2, but yeah, they're just directly proportional. But then if I try and, that same pattern doesn't really apply when I try and look at the next lines?
Well, from here to here, the concentration of the CHCl3 isn't changing, right? And going from this one to this one, it's doubling, but this one is also changing. So we're changing both concentrations. They're both having an effect on the rate. So if we take that 0.027 and divide it by 0.0098, it increased by 2.755, a factor of 2.755. And that doesn't make any sense, but we've got two things changing. And one of the difficulties is when you have multiple variables that are changing, it's hard to figure out what's going on. And so that's why we try to control variables in experiments so that we change one thing at a time. Change this one thing and see what happens. Does that help?
So just take the first data points, basically?
Well,
turn out the simplest?
Not necessarily. You have to find two data points where one of the concentrations is the same. So from here to here, this one didn't change, and this one did. So then we know that the change in rate is due to the change in this concentration.
No, I see
Okay.
it. I just didn't.
That's okay. I'm sure there's several other people who didn't see it either. And from here to here, this one is staying the same, and this one's changing. So the change in rate then is due only to the change in this concentration. So good question. Any other questions?